All right, so we're going to talk about the power rule. So we need to remind ourselves of some notation first. This ddx is telling us to take, the derivative with respect to x of f, a function of x, and so we would say something like this. If I put f inside this, square brackets ddx, then I get f prime, the derivative of f. And so I'm just using this notation. I want to remind us of that. Okay, so what happens when I take the derivative of x squared? There's a power rule for derivatives of powers of x. We want to construct a power rule for indefinite integrals of powers of x. Okay, so remember how we do this? We bring the coefficient down and take 1 away from the power of x. So in this case, we would really just write this as 2x, right? So the derivative of x squared is 2x. And we saw this one in the last one, right? So we'd bring 3 down, and then we'd have x, and then we subtract 1 from the exponent, so we end up with 3x squared. The next one, same sort of thing. So we have 4x, take 1 away from the exponent, 4x cubed. So this is calculus 1 material, and that's how it goes. So it's pretty easy to follow rule once you see how it works. And the general rule looks something like this. If I have x to any power, then I can pull the exponent out front as the coefficient, and then take 1 away from the exponent, and that becomes my new exponent. So what we want to do is to end up with some formula of this form, but for integrals of x to some power. All right. So what does the the antiderivative, the indefinite integral look like for this kind of function? Okay, so let's start with x squared. It's a good place to start. So what should we be doing? So what should happen here? Well, it's the opposite of taking the derivative, right? So what happens when we take the derivative? So we would need to undo taking the derivative. So when we take the derivative, the coefficient goes up front, right? But then also the exponent counts down 1. So one thing we know is going to have to happen is we need to start with something like x cubed, because when we take 1 away from that exponent, we want it to be x squared, right? So let's just see if that works. So here's a question. Does x cubed work? The answer is going to be no, but let's see how far off we are. I mean, it's close, right? So if I take the derivative of x cubed, we saw before, we just get 3x squared. So it's close, right? So the thing we want, the answer we wanted was just x squared. So how do we deal with the fact that we have this 3? And the way we deal with that is pretty simple, because what's happening here? 3 is being multiplied. So it's what we want, times 3. So there's an easy way to get rid of 3 with multiplication. You can either divide by 3 or multiply by 1/3. So what to, sort of get rid of this? I'm going to multiply times 1/3. And so what happens if we put a 1/3 here? And I'm going to put a plus c out here too, because it could have been any constant. So the answer is no, but almost. So now let's check the other one. So does 1/3 x cubed plus c work? We'll drop the 1/3 since we did on the first side. I mean the plus c. Okay, so let's check. So let's take the derivative of 1/3 x cubed and recall some properties of the derivative. Remember that the derivative doesn't touch constant multiples, so we can pull the 1/3 out and then think about what happens to x cubed. The 3 comes down, x is there, and then we take 1 away from the exponent, so it's 3x squared. And then what's happening now is we have 1/3 times 3 x squared, and 1/3 times 3 is 1, so we just have x squared. And so this does work. Great. Okay, so let's see, can we do the same thing? Let's take the integral of x cubed and see if we can see a pattern here and come up with a formula. So x cubed, we know we got to go up 1 in exponent because when we take its derivative, it's going to go down 1. We know this is probably not going to work because if we take the derivative of plane x to the 4th, what do we end up with? 4x cubed. So not quite right, but close in a similar way. And so before we had to multiply by 1/3, so now we can multiply by 1/4 to get rid of the 4. Okay, so going back up here, what we really want is 1/4, x to the 4th. And so let's check this. This is not quite again. So let's check this one. If I take the derivative of 1/4 x to the 4th plus c, oh yeah, we're dropping the c, so let me get rid of this. Just remember that, if we take the derivative of plus c, it's always going to be 0. Okay, so let's take the derivative of this. So 1/4 again stays the same because take the derivative of a constant multiple, it doesn't change that, and then the 4 comes down and I have x cubed. Here, and the same sort of cancellation happens. I have 1/4 times 4, which is 1, and so really I'm just left with x cubed, so that one works. Okay, so then the question is, can we come up with a general rule here? So let's write some of these down. So far we've seen that if I take the indefinite integral of x squared, I have 1/3 x cubed. If I take the integral of x cubed, I have 1/4 x to the 4th. Let's try to guess what we'd get if we take the antiderivative, indefinite integral, of x to the 4th. Well, what appears to be happening here, so similar to the derivative, I'm doing something in the exponent, but I'm adding 1 instead of subtracting. So let's go ahead and say this is going to be x to the 5th. And then how am I choosing my coefficient? Well, I'm trying to do the opposite of derivative, and the derivative is going to multiply by 3, which is the exponent you end up with. And so the antiderivative should multiply by its reciprocal, 1/3. And so 1/4, and so this we could guess would be 1/5 and would be right. So think when we take the derivative of this, it's going to be 5 times 1/5, which gives me 1. I'll take 1 away from that, which is x to the 4th, and that's exactly what we want to end up with. Okay, so then what's the general rule here? I have x to the n. So what do I seem to be doing? So each time I'm adding 1 to my exponent, so my new exponent's going to be m plus 1, right? So whatever this is, plus 1, 3 plus 1, 2 plus 1, 4 plus 1. And then my new coefficient is just going to be 1 over that new exponent. So my new exponent is m plus 1, and I just do 1 over it. And so this ends up being our power rule for antiderivatives.